So this is an exercise where we want to design a level translator using constant current bias and diode. We have already seen what is level translator. Translator is a circuit or is a black box or is a magic box which translate the DC content available in your signal to zero. It shift the DC content to zero, or it works as a blocking capacitor, right? In IC technology or in differential amplifier or during op amp, when we design our op amp, the level translator is a third stage of that op amp, and it shifts the DC voltage available at the second state to zero. So for this, we need to design this. We need to find out the value of R1, we need to find out value of R2 and R3. So this design is called, I would say, constant current bias. We have already seen this constant current bias with diode, right? This constant current bias can also be made through resistors. We replace these two diodes with resistors, then it will become constant current bias source with resistors. But here we are using diodes. You are all familiar with the why do we need these diodes. So I'm not going in detail. So here we are assuming that the voltage drop across these diodes are VD, they are forward biased, voltage drop across the base emitter is VB, and all this value we can assume that VD is equal to VB is equal to 0.7 volts. Current through this resistor is I, current through these diodes is ID, and current through this the base of the transistor is IB. And we assume that the current through this resistor R3 and R1 is almost equal, and this is IE1, this is IE2, and see, IE2 must be IE1 plus this current IB. But this IB is very small. We know it's order of microampere. So we ignore this, right? We ignore this current, and we say that IE1 is almost equal to IE2. And our aim is that we can always design. We can always choose our values of R1, values of R2 and R3. These R3 so that we get a desired amount of emitter current. Here we assume that our I1 and IE2 is 1 milliampere. It will make the calculations very easy. We will see it later. If we can design this constant current bias circuit to provide IE2 of 1 milliampere, we will see that in order to get 0 volt here, what should be, we should assume that this is also 0.7. All are silicon based transistors and diodes, so we can assume that it is 0.7 volts. So what should be the value of R1 so that we get 0 volt here? If you see that what is the value at the emitter of transistor 1, it is 6 minus 0.7, right? 6 minus 0.7, which is equal to 5.3 volts. We want here 0, and through this is 1. So as you can see that R1 will be 5.3 divided by 1 milliampere, or it should be 5.3 kilo ohms. But next is how can we realize this IE1 equal to 1 milliampere? For this we have to come to this constant current bias circuit. We have to analyze this. For this we have to first find out what is the emitter voltage of this. And emitter voltage of this is base voltage of our transistor 2 minus VBE, correct? Because VB is 0.7, and it is, if we are assuming that this is the base B2 and VB2 is the voltage here, so there is a drop of 0.7 volts, so VE2 will be equal to VB2 minus VBE. Next, we have to find out what is VB2. VB2 is this, right? So if you just see this path, we travel through this path, and this is VB2. Let's do it a bit. This is VB2. We are assuming that this is VB2, and then this is a zero point 0.7 volt of. So you can see that this is a zero point 0.7 volt, zero point 0.7 volt diode, and this you are connecting with minus 10 volt of supply, so minus of this, and this is grounded, right? And we are assuming we want this to be some VB2, right, which is above ground. So if you apply KVL, you can also apply KVL here, and you can see that VB2 will be equal to 1.4 minus 10. So VB2 will be equal to minus 8.6, right? Minus 8.6. So you can apply KVL or just see that voltage drop across this is VB2, and you are assuming that it is more than VB2 than ground. So you can also assume it, like you can think that this is a battery which value you want to find out, and this you can find out by applying KVL that VB2 is minus 8.6. So VB2 is minus 8.6, VB is 0.7, so uh, it would turn out that minus 9.3, right? Minus 9.3 volts. So here minus 9.3 volt is present, or if you put a voltmeter here, you will see that you have a minus 9.3 volt here. And we want a current of 1 milliampere through this resistor. So it is VA2 and the current is 1 milliampere. So what should be the value of R3 is voltage across R3, voltage across R3 divided by current through R3, right? Current through R3. So voltage across R3 is VE2 minus of VEE, and current through R3 is 1 milliampere, which is, we have assumed that we want 1 milliampere of current. So VE2 is minus 9.3 plus 10, 1 milliampere, which is equal to 0.7 K or 700 ohms. Correct, 700 ohms will be the value of R3 if we need 1 milliampere of current through this arrangement, which is a constant current base. Now, how should we choose the value of RT? We have found the value of R1 and R3. How should we choose the value of R2? So here few students make mistakes that they write I is equal to beta times IE. And they assume that there is some value of beta, but they forget that I is not equal to beta I1. In fact, IB is equal to beta I1, right? If you see here, I is the current through R2 is ID plus IB, and IB is almost equal to beta IC. So in fact, we don't need value of beta here in order to solve the problem. We can just assume that our I, we want I to be equal to 1 milliampere, or I is equal to the same as IE1, which is 1 milliampere. So what should be the value of R2? Since we know that VB2 we know, right? VB2 we have just find out that VB2 is minus 8.6, right? This. minus 8.6. VB2 was minus 8.6. So resistance R2 is voltage across R2, which is 0 minus 8.6, because this is 0, this is minus, so current will flow like this. Voltage across R2 is 8.6 and current which we want is 1 milliampere. So what should be value of R2? R2 should be equal to 8.7. So if we choose R1, R2, R3 as 5.3K, 700 ohms, and R3 as R3 is 700 ohm in fact, and 8.6K as value of R2, we can get 0 volt DC here. Similarly, you can also assume I1 is equal to 2 milliampere. Then you will see few differences that are according to the availability of your register. Sometimes you can make the value. We have chosen the value of I1 as 1 milliampere because it drastically simplifies the calculations and it gives you the understanding or the how to select these values. So that is why I have chosen I as 1 milliampere.